Classical mechanics. Today I will be talking about the main philosophy or the main backbone of classical mechanics, what it is all about. And to understand that, we first need to know the meanings of the word classical and the meaning of the word mechanics. Well, if I separate these two, the word classical means at first that in this regime we are dealing with velocities very, very less than light, the velocity of light. Velocity of particles are negligible with respect to light, and we can write that as v divided by c is almost 0, very close to 0. And if it is not the case, then we will be needing spatial theory of relativity to deal with the transformation of coordinates in different reference frames. But when velocity is negligible with respect to light's speed, in vacuum obviously, that is 3 into 10 to the power 8 meters per second, we can use very firmly the Galilean transformation between coordinate systems of two different inertial reference frame. And in this case, the time is absolute. This is the first criteria, such that spatial theory of relativity is not playing any tricks with us. The second criteria is that the length scale in which we are calculating our equation of motions and solving them, it should be sufficiently large such that there are no quantum effects. No quantum effects. You can say that in other words, I can say that this means that we are dealing with macroscopic world or macroscopic length scale. And obviously, if we are dealing with length scales small enough, particles small enough, then we need quantum effects, we need quantum mechanics to explain their behavior in nature. And the third one is that the space-time is flat, that means gravity is not strong enough. That means, in other words, gravity is not strong enough. And this exactly means that we can easily use the Newton's law of gravitational force, and without making any mistake in this regime. Well, classical mechanics is not much used in case of gravity. Well, it is used on the exact accurate length scales. But if gravity is strong enough, then the space-time becomes curved, and then we will be needing the geodesic equations, etc., or the general theory of relativity to understand the motions of particles. So these are the three conditions. If they are satisfied, then we call the system to be in a classical regime. And well, mathematically, this is the meaning of the word classical. In physics, if you have noticed that every time you say classical mechanics, you consciously or subconsciously mean these three criteria to to be held. And now the word mechanics. The word mechanics this tells us how a state evolve with time. Another new word, state. So mechanics tells us about the laws according to which a state evolves with time, or the equation of motion. But at the first place, what a state is, we need to know the meaning of the word state. To understand the meaning of state, we first have to look at simple systems. And the meaning of state is hugely dependent upon the system we are dealing with. Suppose we have a system of a coin. And we are tossing the coin, or the coin is lying on the table, and we are saying we are interested in knowing which side of the coin is facing up. Is it the heads or the tails? And that's all we are interested about. So in that particular system, and according to our own interest to look into the system, we can say that in this case the state is this is either heads or tails. It's kind of like a Boolean system, true or false, 0 or 1, heads or tails. So in this system, the state exactly means which side of the coin is facing up. If I say that my coin is in the state heads, that means heads is the surface of the coin that is facing up. Pretty good. And in this system, if there is a mechanics, there is some force, there is some evolution with time, that such that a person comes and flips the coin every second. So we can say that how the state evolves, if at suppose time equal to t0, the state is heads, then time equal to t0 plus 1, that means after 1 second the state will be in tails. In a single equation, we can say that the state at some time plus 1 will be equal to the state at time t with a bar over his head. If you know Boolean algebra, then you will find this pretty intuitive, because a bar or a knot that converts a heads into a tails and a tails into a heads. Then in this system, this equation will be called the equation of motion, because it tells us how the state evolves with time. Well, our understanding of the word motion is very different. It deals with particles moving around, but you can say that this is analogous to the equation of motion. Similarly, if our system is a dice, then my state will be, and we are interested in the side of the dice that is facing up, then my state will be one of these 6 numbers. And we can define some laws that how the dice is evolving with time, how the face up surface of the dice is changing with time, if it is changing at all. That will tell the mechanics of that system. So a state, in rough words, a state is sufficient information to know the system, the current situation of the system, and the mechanics tells us about how that situation changes with time. That's all. So, in case of classical mechanics, we are interested in systems of particles. So now our system what can I say? Particles. So what will be my state in this case? To understand the state in this system, we have to understand, we have to first acknowledge what we are interested in knowing about the particles. We want to know how the particles move with time. So if we want to see how they move with time, intuitively, we have to know their position. Suppose then my state will consist the positions of the particles. Just a minute. The positions of the particles. But a state should also have enough information, enough data, so that we can find the same state in the next instance or after some time. Suppose we know the positions of the particles at some time t, we are interested in knowing the positions of the same particles at some other time, suppose t prime or t tilde. To do that, we also need the information about the particles, how their positions are changing with time. And that information is stored inside the velocities of the particle. The velocities tell us how the particles are moving, in which direction, and in how much speed. So, the first time derivative of positions is also needed. But velocities not necessarily are constant. Velocities can also change with time, and we should have enough information such that we find the change in velocities too. So one can argue intuitively that we should also know the second derivative of position, that is the acceleration, to understand how the velocities are changing with time. And in the same logic, one can also argue that we also need the third time derivative to understand how the acceleration is changing with time, the jerk. One can also say that we need the fourth time derivative or the snap, and so on. So do we need to know infinite numbers of time derivatives of position? Because we are not guaranteed that any time derivative of positions will be constant such that the next time derivative will be 0. We are not guaranteed that. There can be motion where none of the time derivatives are 0. So this is infinite amount of information, infinite amount of data. How will we collect it? We are in danger. Fortunately, nature is not that cruel to us. And Sir Isaac Newton realized that thing with his equation, with the first equation of motion. He told us that force is something that is equal to mass times acceleration. you need to remember that m is constant. If m is not constant, then there will be another term with the time derivative of the mass. So, for constant mass systems, force is equal to mass times acceleration. This equation changes the picture, how we look at a state, because we are now interested in knowing how much force is acting on a particle to know the acceleration. So, if we know how much force is acting on a particle, we will know definitely the acceleration of that particle. And in nature, our forces, they mainly depend upon the positions and the velocities. For example, if you take gravity, Newtonian gravity, then it is force equal to gravitational constant times m1 m2 divided by r square. R is the position, so it depends upon the position. If you take the Lorentz force, it is force equal to q times E plus q times v cross b, that is dependent upon velocity. So, if we know the position and the velocity of a system of particles, then we will know about the forces acting inside the system of particles. And if we know the forces acting inside the system of particles, then we will also know the acceleration happening to each particle, the acceleration of each particle. So, this changes the picture. If we know the acceleration, by default we know the next time derivative of acceleration, that is the third time derivative of position. So, if we just know these two and forget about these all things, the acceleration, the jerks, the snaps and so on, then with just these two information, we can know how much force is acting on, and we will know how much acceleration is there. And if we know the acceleration exactly, that means we will know the other time derivatives. Mathematically, you can say that the Newton's equation of motion, or the equation of force equals mass times acceleration, this is a second order differential equation. And solving a second order differential equation, we need two boundary conditions or initial data. So, with just the positions at some time t naught and the velocity at some time t naught will be enough to solve this differential equation and understand the trajectory of the particle. So, nature is not that cruel to us, and just by knowing the position and the first derivative of position, that is the velocities, we will know the forces, we will know the acceleration, and we will know the trajectories of the particle, and that is all we want to know. That is all classical mechanics is all about, to know how the particles are moving, to know how the positions are changing with time, and this is enough to tell us how the positions are changing with time. And even in different formalisms, even in Lagrangian formalisms, our Lagrangian depends upon the generalized coordinates and its time derivative. And also it can depend explicitly upon time if we are talking about open systems. Even in this case, due to the same reasons, we only need the first derivative of coordinates. And fun thing is, not only Newton's law, but all the laws in nature, they are second order derivative. They are second order differential equations. In quantum mechanics, the Schrodinger equation is a second order differential equation. In GR, the Einstein equation is a second order differential equation. In any cases, the equations of motion, they are second order differential equation. Well, the Schrodinger equation is first order in time and second order in space. however. So that's the beauty of nature, and that's why we are saved from trying to calculate all the time derivatives to get enough information to find out the mechanics, find out the laws. But the laws are in a way that we only need to find out the first derivative. If Newton's laws were incorrect, if force depended upon mass times velocity rather than acceleration, this was predicted by Aristotle before Newton, then world would have been different. Then we will be only needing the positions to solve the equation of motion. We will only need the positions, and then in that case our states will be consisting of only the positions of the particles. This is called the Aristotelian mechanics. Maybe someday I will talk about Aristotle's law. And even if force depended upon the third derivative of position, then we will be needing even the second time derivative of positions to know sufficiently enough, to calculate the laws of motion and to calculate the trajectories. And in this case, there are some problems. There are some instabilities in third order derivatives. So yeah, that's the beauty of classical mechanics, and that's how we do it. We get the initial informations and we solve the equation of motion. And yeah, so today's video is all about that and why we need only the first derivative of time. And yeah, so bye.